So this is indeed, as Monique indicated, about timing systems and perhaps seen a bit on internal combustion engines. As you will be aware of, the automotive industry uses four-stroke engines where basically first stroke is get the air in the engine, compress the work stroke, and then get the burn gases out into the tailpipe. As you can see in this illustration, this is a very intricate interplay between the piston moving up and down and the valves opening and closing exactly in time, where that timing is of essence for the best fuel economy of the combustion engine. Now, to keep the movement of the piston and the valves in timing, in synchrony, there is a timing system, which in most engines is being laid out with a timing chain that runs on a sprocket on the crankshaft, and that drives two camshaft sprockets, the camshafts, with lobes that operate the valves to get the air in and out the engine. Now, this timing system utilizes some essential plastic parts in order to safeguard its failure-free operation. So these would be wear faces, which you see on the fixed guide and on the tensioner guide here. Those wear faces are in direct contact with the chain that runs at high speed over these plastic guides. The fixed guide on the right-hand side here is directly bolted down to the engine, and it has a bit of curvature to ensure that the chain and chain dynamics don't lead to what you could consider a piano mode string, where there would be massive lateral motions of the chain. Those motions would break the chain if they would run into high amplitudes. On the left-hand side, you see a tensioner support arm, again with a wear face clipped on. This tensioner support arm needs to take up any chain lengthening or chain wear during the use of the engine, where if the chain wears out or wears, it will lengthen, and then this spring-loaded, hydraulically damped chain tensioner basically pushes in the tensioner arm deeper into the chain path so that the chain tension remains within check. Key metrics of this system: the chain speed at around 3 to 20 meters per second, which is appreciable speeds. Chain tensions very dynamically changing between 200 and 2000 newtons, with every compression and work stroke changing between two extremes. An engine life laid out for at least 3,000 hours of service time, with high chain dynamics and potential lateral motion that needs to be kept in check with these guides and tensioners. Important are regarding chain on guide wear. It needn't be zero, but it needs to be acceptably low. So this requires wear-resistant materials. It is of utmost importance to lower the chain on guide sliding friction for contact with both these plastic parts to an absolute minimum, because low friction ensures a high fuel economy, which in turn ensures a low CO2 emission, which in turn ensures low emission penalty for the cars that are brought on the market. So with this overview of an explanation of the application, I would like to kind of take the next step to the slide, where you see that, yes, we have chain guide wear faces clipped onto a support arm. The chain guide wear faces need to be durable against abrasive wear, need to be robust against chain slap and pitting wear, and of utmost importance, need to provide the lowest possible friction for best fuel economy. These support arms on which these chain guide wear faces are clipped on need to provide stiffness, mechanical stiffness, They need to provide a low weight, because this is a highly dynamic part, and a low weight implies a low inertia, which implies lower required spring forces to bring the support arm and guide back into contact with the chain, which in turn enables lower chain tensions overall, which basically also helps to lower the friction losses of this system. Because the chain tensions are fluctuating so intensively, this is a highly dynamically loaded part, and for that reason, the fatigue strength of this part and the materials that they're made of are of essential importance. Focusing on low friction for fuel economy. That has been brought about in most of cases by just adding PTFE to the plastic. So let's pause a bit and look at what is PTFE. Well, it's a synthetic fluoropolymer where tetrafluoroethylene is being polymerized, and it's a fantastic material. It is chemically very stable. It brings low stick, low friction, and one of the applications that are well known are non-stick cookware. In plastics, in engineering materials, one is using micro-powdered PTFE, which are then compounded into the polyamides or plastics in general to reduce the surface friction of this material. So why is it so widely used? Well, it's a very powerful additive, and it is highly effective in reducing friction and improving wear in these applications. However, there is a downside to the almost chemical inertness, and that is the following. There is a grave environmental impact because in the making of micro-powdered PTFE, one has to either irradiate or thermally treat it in order to facilitate the milling of the PTFE into these micro powders. The irradiation process is a high energy radiation process that creates all kinds of side products that are unintended. One of these moieties is perfluorooctanoic acid, or PFOA in short. This is produced during the manufacturing of these PTFE, irradiated PTFE powders. PFOA is just one of the chemical components in a larger family of PFAS compounds, where PFOA is the octanoic acid. In the family, you have nonanoic, decanoic acid, and the irradiation process isn't very specific. So you create many more of these concerning chemicals in making PTFE powders. Because PTFE is so chemically and biologically stable, these materials don't easily break down. And when spilled into the environment, they leach into the groundwater, they find their way into the drinking water, they find their way into the food, for which the water is being used for irrigating. And then getting into the food, they make their way into the human body, and that is where they accumulate. Now, research shows that it may lead to many chronic health issues, such as cancer. And the latest indications are that also the immune system is being compromised. And well, I guess everybody knows that in these COVID times, everybody appreciates a well-functioning immune system. This whole situation of leaching into the groundwater water bodies has led in some locations to these type of warning plaques that you can find in the outdoors, which basically state that it is perfectly okay to enjoy swimming and boating and hunting and catching fish. But what you shouldn't do is eat the game and the fish that you catch, because the waters are polluted. These chemicals have accumulated in the game and fish, in the wildlife, and it's not a good idea at all to consume these products. And it's the gravity of this situation where global regulators are taking action. For instance, the European Environmental Agency is really restricting any product that contains PFOA to a level as low as 25 parts per billion. And those materials above that 25 ppb will not be allowed to be used within the European Union very soon. The US EPA is working on legislation for the United States. The Japan Ministry of Health, Labor and Welfare is also restricting the use of these PFOA containing materials. While this is well in progress and restrictions are being applied, there is the onset of discussions not just to ban the PFAS family of chemicals, but to perhaps look at a ban of PTFE entirely in the future. Now, this is a situation where I would like to call your attention, because in the value chain where people produce friction-improved materials with or without PFOA, where the molders start to mold parts, where these are shipped to the assembly lines where vehicles are assembled, once brought to market, they will be brought to market for a period of 5 to 7 years before an overhaul or a redesign is being considered. So just imagine that you're today in the situation where you need to either select a material which does or does not contain PFOA or PFAS in general. If you would select such a material, you will run the risk of needing perhaps to reapprove or re-PPAP new materials if these materials contain PFOA or PFAS, because in the years to come, the legislation will intensify on this. And that is indicated with this arrow here. PFAS regulatory actions are being considered and are ongoing in many countries. And for the foreseeable future, the same might hold for PTFE containing materials. This has led DSM to be extremely cautious, and DSM, with sustainability as one of its main missions, product stewardship at DSM for the last decade has ensured that any new product we bring to market has been scrutinized for all of its components to be safe and sustainable for use. The result of this is that, yes, we have developed a material, a polyamide 4,6, that contains PTFE, but we've made sure that the PTFE that we've chosen does not contain these suspect chemicals like PFAS. The latest product that we are bringing to market, and we'll discuss that in more detail in this presentation, are even PTFE-free polyamides. DSM has found additives that are more effective than PTFE and therefore bring you a very attractive combination of properties. As a third step in sustainability at DSM, we're bringing bio-based polyamides, polyamides with a renewable content in the form of bio-based, mass-balanced, certified polyamides, and that is the polyamide 4,6, which is being used in the HCl3 that we're bringing to market now. So if we look at the part of the portfolio of DSM where it comes to timing systems in direct contact with the chains, our latest addition to the portfolio, the the material that is being launched and is already specified in some of the engines that will go in production shortly is HDR3-W. It is the ultra low friction, and it is the lowest friction material currently on the market. As indicated, we found better additives than PTFE to ensure that this low friction is being brought about in a robust way. And as a third aspect, this grade is certified bio-based mass balance in content. It has an extremely low carbon footprint, and we'd love to talk more about the LCA aspects of this latest addition to our portfolio. The current workhorse when it comes to low friction is Stanyl HDR2. It does contain PTFE, and it is very effective in bringing a low friction. And the PTFE that DSM is using is free of PFAS and or PFOA. Free means here that this is below the detection limits on the PTFE powdered additives. And it is therefore that DSM is happily certifying that this HDR2 material is totally REACH compliant, and we'd be happy to certify other non-European REACH compliancy as well. The workhorse for over 3 decades are the 2 grades, TW341 and TW441, which bring the benchmark of highest robustness, very low pitting wear, very low abrasive wear, no additives other than heat stabilizer. This is the pure PA46 as the high crystallinity, extremely robust polyamide. For those of you who appreciate a bit more quantitative underpinning of our low friction claims, in this graph you see on the y-axis the coefficient of friction, on the x-axis the chain speed. And these are the results from friction testing in the way that is being shown here. So here you see 2 sprockets, the chain that is being driven by these 2 sprockets. This top sprocket can be pulled up to maintain a 350 Newton chain force. The chain is running over a plastic sample in the sample holder here, which is mounted on a bending beam, where in one test we can measure both the sliding friction force as well as the normal force exerted by the chain on the plastic. So as indicated here, we're measuring directly the friction force and the normal force, and the coefficient of friction is then the friction force divided by the normal force as per the definition. So that is being plotted on the y-axis in this graph. We measure this at typical fired engine internal temperatures in commercially available engine oils. The results on the x-axis basically start at idle temperature, 850 RPM typically on engines, and then expand the full range of RPMs, where the most relevant RPM range is between idle and roughly 2000 RPM, which would be here around 4 meters per second. What you see in this graph is that, yes, you have the incumbent PA66 high molecular weight. Slightly lower friction is being had from the TW341 because of the higher crystallinity and higher stiffness of the PA46. We've made a significant improvement in lowering the friction with the development of our HDR2 material, PTFE containing, made out of safe PTFE, clean PTFE. The latest innovation that we are bringing to market is the HDR3-W, which you see in the green line here. And indeed, in the highly relevant RPM range of the engine, this again gives a significant step down in friction losses in these timing systems. Looking at the complete portfolio that DSM brings to market, and we're proud to claim that we have a full slate of grades that covers all your needs in timing systems. If we break down the components in wear faces or clip-ons, in one piece, and in the structural support arms, let's look at the design focus that you might have in wear faces. You might want to design for ultimate friction reduction. And if that is the case, your best-in-class material is the HR3-W. It gives you ultra-low friction without the hassle and concern and potential risks of PTFE containing grades. Next best is the HR2, which provides you a very competitive benchmark so far, low friction grade. It contains PTFE, yes, but it is, as I explained, a clean PTFE without any concerns on PFAS or PFOA. If you look at a design focus where you want to bring about robustness in your timing systems, then the straight PA46, TW341, 441 grades would be your materials of choice. The higher molecular weight version of TW441 will give you really extreme pitting wear. The TW341 regular molecular weight, excellent pitting in combination with excellent abrasive wear. If you're designing for cost mitigation, we have the standard PA66 high molecular weight heat stabilized S240CH material. If you're looking into the one piece, typically you're not looking at the more expensive friction optimized grades because these parts are a factor 4 larger easily than the clip-ons, so they use more material. Here again, you have the workhorse materials for robustness, the cost mitigation, but here I would like to extend the grade list and ask your attention and appreciation for a high molecular weight heat stabilized PA6 material. This is a very attractive material if in the case your system benefits from chain snubbers. Chain snubbers would be chain guides that do not see continuous contact and sliding motion of the chain. Chain snubbers would be slap guides where these in extreme dynamic situations the chains might show extraordinary lateral motion, and these non-contact slap guides will curtail that lateral motion that could potentially be devastating to the chain. The other application are the support arms, where you could focus either on robustness or on cost mitigation. Let's focus a bit on robustness. One of the grades that we think deserves more attention is our 40 ppA glass fiber filled 50 or 60%, the MX53B or MX54B grade names. They bring you ultimate stiffness because these PPAs have a TG of at and above 140 degrees. So in the fired engine regimes, those will run below TG, and you can benefit from below TG higher stiffnesses for these materials. These would really be materials that would bring you a lighter weight alternative to stiffness, the ultimate stiffness, perhaps replacing your metal brackets. The big benefit of these much lighter plastics is, as I've indicated before, that this enables you to tune your system in further ways at lower overall running chain tension, which would greatly benefit your friction losses, reduce your friction losses, that is. Looking at robustness, we have the ultimate stiffness, superior fatigue and stiffness, PA46 grades in glass fiber 50 and 60%. And then the second option here, if you look at cost mitigation, yes, we have the PA66 glass fiber 50, the S223HE0, but I would like to call your attention to a PA6 GF50. The fatigue strength of these PA6 GF50 grade can easily compete and surpasses the fatigue strength of these PA66 GF50 types. The grade is called Aculon K224HE0 and is a welcome option and opportunity in these very volatile times where PA66 supply lines face the challenges of availability. What DSM has been bringing to market is proven performance. We've been the #1 material for timing drive systems for the last 3 decades. All the OEMs, all the global tier 1s are using DSM materials in one way or another to bring about the ultimate properties in timing systems. DSM is designing, has set the pace of designing low friction materials. We're basing these developments on material science. We do understand how friction comes about. We do understand how to optimize materials from a recipe point of view to bring out the best synergy with the oil additives that lubricate these systems in the fired engine. We have been bringing best-in-class strength and mechanical performance with our superior grades that I just mentioned in the portfolio overview. Sustainability is at the core of the values and mission of DSM as a global company. DSM's commitment is to take the uncertainty out of your compliance issues. We've brought materials to market, I mentioned the HER2, where we provide letters of conformity so you have no concern about REACH and other limitations. We're removing substances of concern because it's the right thing to do. As I mentioned, this is our product stewardship paying off for the last decade or two. We're taking sustainability at heart. We've developed bio-based and recycled alternatives to our existing portfolio. This is where our HER3-W is based on a renewable resource, bio-based, mass balanced, and it is being certified, and you can take these certificates up the value chain all the way to the OEMs. Last I want to mention is that DSM has been buying green energy for already a number of years to reduce the environmental impact of our production operations. And that helps to lower the carbon footprint of all the grades that we are bringing to market. In summary, Stanyl HER3-W, the next generation solution for chain on guide systems with a focus on best fuel economy, lowest CO2 emission, lowest penalty. We're bringing to market a PTFE and therefore PFOA-free grade. HER3, we've found better additives than PTFE to reduce friction. It is built on a bio-based mass-balanced PA46 base resin, and I've not touched upon this in great detail, or in any detail for that matter, but the HER3-W is improved in processing when compared to the PTFE containing alternatives in the market. With that, I would like to thank you for your attention.